Okay, so thank you very much. So, wow, it's really amazing to be speaking here, you know, and maybe this is like 800 years later, I'm explaining cosmology, like you might have sat in this room and heard Robert Grosseteste explaining it. So I hope I have the details right. I have a vision that there'll be a voice coming from just the screen behind me, from the bishop's chair, going, "No, you've completely misunderstood that point." So I hope I'm doing justice to the amazing work that he was able to do, understanding the origin of the universe. So what I'm going to try and do in my talk is to look at how we understand the universe and to compare how the understanding has developed over time and how we've tried to answer some of the fundamental questions. Like, was the universe created? How is order established in the universe? And I'll try and compare what we think happens today with how Robert Grosseteste would have explained it, and maybe even earlier peoples than that. So, we're going to talk about cosmology. That's always quite a big subject. And we want to ask some big questions, okay? And we want to try and understand, where does it all come from? I won't have time in this room to talk about the other things. You know, how will it all end? Will there be a big crunch? Will we just die out and disappear into darkness? That's a fascinating question too. And I certainly haven't got time for what's it all for. Maybe Bishop Grosseteste would have had much more to say on that. But what I want you to think about in this talk is how the kind of questions that have maybe been asked since very ancient times have developed to how they were addressed in cathedrals, in the chapter houses like this, and to how we might address it today. So I have various different roles. I'm currently studying at the Institute of Advanced Study, meeting with people that study ancient civilizations or aboriginal civilizations and understand the stories that they tell about the origin of the universe. We've been discussing in the Robert Grosseteste in the Ordered Universe project and how that would have been, the cosmos would have been understood in cathedrals like this. And I'm also PI on a project to understand the universe today that uses some of the largest computers in the world to try and calculate how we now think the universe is created. And we kind of have amazing tools today, but I'm ever so amazed at what Robert Grosseteste could understand about the origin of the universe in his time. Okay, so I want to frame the question, the talk, in terms of an ancient question that was argued between Aristotle and Plato. And Plato had this idea, wrote a book describing a discussion describing how the universe was created. And I think in this book that it's really a summary of older ideas from Pythagoras, so even older Greeks, and it has a lot in common with, I think, almost all societies. And in this, the idea is that the universe exists in some kind of chaotic state, but that a godlike figure, the demiurge, creates the order that we see in the universe today out of this chaos. And so, essentially, the argument that you might use is you look at the world around you, it looks very perfect. It's got lots of order. There's an order on earth. There's an order in the heavens that you see. How was that order created? And then an obvious answer is that some godlike figure created this structure. And so this is the story that Plato retells. But slightly later, Aristotle is very unhappy with this idea. And his problem is that if you try to begin to apply logic to these problems, how, he asks, can something that can be modified and changed and created be perfect? And he stumbles across something that we now think is very important in physics, that we call the second law of thermodynamics, but is essentially the idea that things tend to decay. So over time, things become more and more disordered. And so Aristotle's answer to this question is, well, anything that's created would decay over time. The universe still looks perfect, so it was never created. It's always been there. It's always been in this structure. So in the Hellenic philosophy, there's this contrast between these two viewpoints, between a created universe and one that has always existed and always been perfect. And into this framework, I'd like to look at how the work of Robert Grosseteste fits in. So he inherits a lot of the ideas from Aristotle, but clearly he's Christian, so he can't accept this idea that the universe has no beginning. So how is he going to get out of this problem? Now, when we started work on the Ordered Universe project, I started with the preconception that if it was done in medieval times, it would clearly be very simplistic, and a lot of what happened in the universe would have been thought of as magic. And so this is a frame from the Bayeux Tapestry, okay, illustrating William on this side, Harold's household on that side. They have the advisors, the astrologers, and initially you look at this and you think, well, it's all about mysticism, and they're worried by this comet in the sky. Now, so my starting viewpoint would be about the mysticism of this, and that people would just take this as a bad omen. But I now have a much deeper understanding that there's actually a really big reason that comets are a major perturbation to the order of the universe, because they imply that there's change in the heavens, which you would have thought were perfect if Aristotle were right. So maybe this discussion here is actually quite an intellectual, high-level discussion about the nature of comets, and that the starting point for your view of the medieval universe needs to be very carefully thought out. Okay, so I'll skip over the movie. The other thing that often people look down on in these early cosmologies is the idea that the universe is geocentric. And by that I mean that there's an Earth at the center of the universe, that the Earth is here and that the planets orbit around on circular spheres around that. Now, and then Copernicus comes along, realizes that you could make a better model of the universe by putting the sun at the center. Having the Earth orbit around the sun would explain much more of what you see of the motions. But that's not actually a new idea, amazingly. That Pythagoras had the idea of putting the sun at the center and having the Earth orbit around the sun. And those arguments were vigorously debated. So I think if you were standing here with Robert Grosseteste, he would have no trouble in convincing you that the Earth was clearly at the center of the universe, and that anybody trying to tell you anything different was clearly stupid. Right? And I think he would essentially have used two arguments. One, he'd have asked you to stop, right? Just feel. Can you feel yourself moving? Right? If Copernicus was right, if Pythagoras is right, you're moving at 1,000 miles an hour, far faster than even the best horse you can buy in the market outside. You're not moving, right? It makes no sense. And you could try out a little experiment. You could get a ball and you could try and stick something on the outside of it, put it on and spin the ball round, and the thing flies off, right? So one reason it doesn't make any sense to have the Earth spinning. The Earth must be still and the heavens spin around you. Okay, and there's another argument as well, that if we were to put the planets that are near us on these circular orbits, they go around their circular orbits. And they stay more or less the same brightness throughout as they travel around the sky. If you want, on the other hand, to have the sun at the center and the Earth orbiting around the sun and the Mercury and Venus orbiting around the sun as well, at some times you will be very close to Mercury and Venus. They should be incredibly bright. At other times, they'll be on the far side of the sun and would be incredibly faint. But you look at them, they hardly vary at all in their brightness in the night sky. And you could think, oh, well, this is because people didn't have a very sophisticated understanding of light. But we know that Robert Grosseteste knew all about how light propagates. He could almost have built a telescope, from what we read in his works. So these two reasons convince you that you must be at the center of the universe. It's also good in that it makes a nice symmetric picture. It looks very perfect, has a nice symmetry to it. We can understand why the Earth is at the center, why if I drop a heavy object, it falls to the center of the Earth. It doesn't go flying off in some strange direction. It's all down to the symmetries of the universe. Okay, so if you were a modern scientist and you didn't have access to a modern telescope, you would, I think, end up agreeing with Robert Grosseteste on this. Okay, now, all right, so I think I have to skip over that. I can come back to that question. But what we were studying then in the Ordered Universe project is a document called De Luce, means on light. And this is really about the origin of the cosmos. And you might think, what has the cosmos got to do with light? Well, Robert Grosseteste is really one of the first people to try to do cosmology as I would do it today. So what I do in my daily job is I take the laws of physics, and then I try to construct those so that I understand the behavior of things here on Earth. I then take those laws and assume they apply everywhere in the cosmos and across the whole of time. And if that's under that assumption, I then try to predict how the universe should form. Now, the amazing thing is that this is exactly what Robert Grosseteste does. He makes an astounding assertion at the beginning of the work about how you get solid materials, the nature of materials. So he's read about an atomistic view of matter, which tells you that matter is made up of very tiny atoms. But he realized there's a problem with this. I mean, if the matter is made of tiny atoms, how do you make a table that's solid? It's the atoms need to be made to have some volume, even though they're tiny and infinitely small. So what De Luce is about is really about the interaction of light and matter, and Robert Grosseteste comes to the idea that it's this interaction, light spreads out infinitely, giving infinitely small atoms a finite volume. Okay, and this is basically what this quote says. In here, I'm not going to try and practice my Latin, but basically it says, the first corporeal form, which they name corporeity, I consider to be light, for by its nature, light spreads itself in every direction in such a way that as large a possible sphere of light is instantaneously generated from a point, provided nothing opaque stands in the way. And so this is the basis of Robert Grosseteste's cosmology. And he goes on and takes this idea of light spreading out and matter spreading out and realizes that this could be an explanation for the origin of the cosmos. And so he continues, so light, which is the first form in created matter, by its nature infinitely multiplying itself everywhere and stretching uniformly in every direction, at the beginning of time, extended matter, which you couldn't leave, drawing it out along with itself into a mass the size of the world machine. Now, this is an amazing idea. So he completely dismisses Aristotle's idea that the universe was always there, and there is a beginning of time, a point, a moment at which the universe starts, and also that the universe starts at a point and then spreads out from that point, okay, becoming bigger and bigger. And the interaction that he supposes between light and matter is such that the matter is drawn out as the light tries to expand. And this is really quite an astounding idea. It sounds remarkably like the Big Bang. And indeed, we wonder whether some of the ideas for the Big Bang came from reading Robert Grosseteste's work. We know that Lemaitre, who was one of the proponents of the Big Bang model, was a Catholic priest. It would have been reasonable for him to know about Robert Grosseteste's work. Okay, so de Luce begins with this idea that the universe is a mix of light and matter, that they spread themselves out infinitely, creating something the size of the world. Well, that's okay. That's quite good. But Robert Grosseteste isn't very happy to just do a little bit of the problem. He would like to create the world as you see it. And so amazingly in the text, he then goes on to make a few more propositions about the idea that the different types of matter are created by, in some way, different combinations of light and atoms, and that this creates a set of the heavenly spheres. Now, there isn't time to go through the original text, our translation, but let me just summarize what these little boxes, which are quotes from the original document, mean. So you start with the light expanding as the universe. There's a minimum density, a minimum amount of matter that you can have, which creates a kind of shell around the outside of the whole world. And you have interesting questions like, well, what's outside the shell? Well, nothing, because you can't have anything there, because there is nothing. And when you ask me later about what's outside the Big Bang model, I'll have to give you more or less exactly the same answer. And so this creates a shell around the outside of the world, and he supposes that this shell that's created somehow emits a new form of light that travels inwards, pushing the remaining matter back towards the center. And as it does so, it creates new types of material of different ratios of matter and light. Okay? And it first forms a shell that's inside that, the shell of the fixed stars, and then we'll get the shell of Jupiter and so on, creating the planets as we go towards the center. Okay, now I'll leave the last point for later, but you can read this in the text, and you can look at our paper that we've produced that that shows how we translate these bits of text into English, but this would be a story. Okay? But what's remarkable about Robert Grosseteste is that the story is so precise and so well defined that we can translate this into something much more useful. So instead of having a story in English, which we've translated from the Latin, we can actually turn the story into mathematics. So mathematical equations like this didn't exist in Robert Grosseteste's time. But so the equations are a modern way of trying to summarize what's said in the text. This is all to do with how the light propagates in this first equation. This is an equation that tells you how the light makes matter move. This is something that Robert Grosseteste can express very simply in that matter is always there. It's not created or destroyed. Actually, it's quite hard to write that in mathematics. And then there are these extra conditions of the possible different forms of light and matter and how those can be combined together. Now, the beauty of being able to render it as mathematics is we can use the power of computers to actually see what happens here. Okay? We don't have to just believe the story, we can see mathematically what happens. And what's interesting is that the effect is rather like a snowplow. You have the light coming in from the outside of the universe, sweeping up material, and it kind of pushes this front of snow towards the center, the front of matter. Okay. And then just to prove that this isn't crazy, I had great difficulty solving this problem on my supercomputer that we have buried in Durham. And eventually I kept getting really fed up with this. I was up late every night because I'd try a new thing and I'd get a slightly different answer. And I knew if we sent this to the journal, that the editor would say, well, it's no good. You know, you have to get the same answer no matter if you change a little bit of the calculation. So I ended up discovering that there was an easy way to do this problem. And it cooperates. And that's geometry, basically. That in order to make my program work properly, I had to find a situation that I could solve using geometry. And of course, geometry, Robert Grosseteste would have been an expert in. So, I don't know whether he would have actually done that, but it's not impossible for him to solve some of this problem, not the full thing, but some of the aspects of it, using the tools he had available. Okay, so I need to move along, but I want to show you this beautiful movie of how the universe was created in about 1230. Well, the universe wasn't created in 1230, but this is how, if you'd been standing here in 1230, you would have understood the creation of the universe. And I've got to click the right button. And so what happens is this is the outer shell, the firmament that's the first perfect form of matter that's created. And as it moves in, it's sweeping up material and pushing it back towards the center. Now, initially, there isn't very much material in the outer parts of the universe because of the way that initial explosion happened. But now we begin to get quite a density of matter, and you can see this thin white ring that's created there. And as it's pushed inwards, we create ever newer forms of matter. And Robert Grosseteste would argue that this one is associated with the firmament, then one is associated with the fixed stars, the stars that don't move. And then as I move in, these are associated with the wandering stars, the planets. And then we'll get to somewhere we'll get to the sun on one of these orbits, Saturn to Venus, Mercury, and then then the moon. Now, something's gone wrong with my mathematical model here in that I have a huge number of planets. It looks very pretty, you know, psychedelic. I don't know whether these colors would have been approved of in church, but clearly there's something wrong here. And the astounding thing to me was when we went back to the text and read what Robert Grosseteste describes about this. He realizes that something has to change. That as the matter is pushed in, the process doesn't continue forever. And so his quote is, "This concentration resulting in dispersal went on in this order until the 9 celestial spheres were completed and condensed into the mass of that, and a condensed mass, the matter of the 4 elements, was concentrated below the 9th and lowest sphere." So he imagines that this process somehow stops and leaves us on the Earth with a strange mix that's not quite separated out into its perfect types of matter, and the things that are left are earth, air, fire, and water. Now, he's quite convinced that this is what's going to happen, and it took us a long time to try and understand how we could translate in the mathematical thing. And then we had another read of the text, and it keeps telling you that the spheres towards the center are less perfect. And you go, yeah, well, this is some religious aspect about how God in the outer parts, these are the most perfect spheres. But maybe, in addition to that, he also means that they're less good at transmitting the light that's coming in from the outside. And so if you include that in the mathematical model, something miraculous happens. So I think this takes a while to start up. I've had to change the way the universe starts, and it turns out that the universe has to start in a quite special way to end up with 9 celestial spheres, to have exactly 9 planets. But now we'll start quite quickly. The planets sort of form much closer together. And then, because of the imperfection of these spheres, they maybe absorb some of the light that's been generated in the outside. So actually it becomes progressively harder to separate out matter into a new form. And eventually this program will have to stop the calculation, and we'll be left with a white part in the center that never gets properly separated out. Come on, computer. Okay, you have to have patience in these universes. See, it's getting so hard. You're managing to push the matter in towards the center, but it's getting harder and harder to do that. And then eventually the process just stops, leaving you with the celestial spheres. Maybe this is what he had in mind. I'm not going to propose he actually was able to do the details of this calculation, but it's to prove that the concepts that he describes are very accurate. And so we're left with the Earth in the center, the Moon, and then the Mercury and Venus and so on out into out towards the fixed stars and then the firmament. Okay, so this is quite an achievement, right? I find it really astounding that this idea, this very forward-looking approach, I mean, now we no longer think the Earth is at the center of the solar system, but given what you knew, he comes up with a very plausible physical explanation, going from describing the world around him to describing the nature of the universe. Okay, so he solves the problem that Aristotle originally posed about the nature of the universe and how, if it started, does it continue? So there's a beginning to this scenario corresponding to something, that initial explosion, but once these perfect spheres have been created, they stay there forever. So it's not a puzzle that we're here, we just happen to be here at a moment when we can see the universe around us. Okay, now I want to move on and contrast what we think of, what Robert Grosseteste's cosmology to how we understand the cosmos today. And I will particularly focus on this idea of the creation of the universe and this problem that things that are constructible or things that can be generated are also destructible. Okay? So how do we overcome that problem today, that philosophical issue? Now, I fortunately last night realized that I'd better tell you what the universe looks like, right? Or else the rest of the talk won't make much sense. So I give you my 30-second bluffer's guide to the actual universe. So the first important thing you need to know is that when you look in the night sky, there are stars. I mean, Lincolnshire must be really quite dark. It's not like trying to observe the stars in London or the middle of Newcastle. And so when you look out into the night sky, you see the stars. Now, it was really Thomas Wright in Durham that realized that when you look at the stars, they're not distributed uniformly across the sky. And in fact, they're all compacted, they're all concentrated in a disk of stars. And so here what you're seeing is a spiral galaxy, perhaps like the one we live in, and this is a flat disk of stars. And we live somewhere boring, like about here. You know, it's not even near the center where there's lots of exciting things going on. We live somewhere near the outer parts. If you live in the southern hemisphere, it's really exciting because you look towards the center of the galaxy and you see all these amazing things and incredible numbers of stars. But we tend to be looking this way, you know, in the boring direction, where there are not so many stars in the sky, and it's not quite so obvious about this being a thin disk. Now, there's an extra slide here. I wonder what, this is just to say. So, I'll inevitably start talking about galaxies in my talk, and when I say galaxies, I mean a collection of stars like this. So, you know, there are maybe 100 billion stars in a galaxy, something like this. Okay, now, you haven't had a movie for a while, so let's have a brief treat of a movie. So what we're going to do is, Thomas Wright had this totally crazy idea that, well, if we lived in one of these galaxies, maybe the universe was full of them. And he had all sorts of crazy ideas about what these galaxies would look like. But it turns out that that's actually a very good description of the universe. It's full of these galaxies. So what we're going to do is we're going to do a bit of space travel. It's quite like the TARDIS in this room, so I think we just have to start the control panel up, and then we could fly through the universe. But unfortunately, that's broken this evening. So what we'll have to do is we'll just take a little movie and we're going to fly into a piece of the universe. So this is a region of the universe. Really, there are galaxies everywhere, but we're going to fly into this part and see what the universe really looks like if we were able to travel in a spaceship. Okay, so here we go. We're going to dip into this. This is a movie made by one of my colleagues in Durham. These are all galaxies that were observed with the Hubble Space Telescope, and they've been put in their actual positions in the real universe. So this really is flying through the universe, right? It's absolutely amazing. And you see just how full the universe is of galaxies like that. And each one of those is 100 billion stars. And you begin to get the impression that not only are we not at the center of the cosmos on the Earth, but actually the Earth is not at the center of the solar system. The solar system is in a very boring place in the galaxy. And the galaxy, well, it's just one of these, right? So we are very much just in a democratic, average piece of the universe. And yet, you know, it has this beauty and order of things being concentrated together creation of planets, stars, human beings able to comprehend the universe is really quite an incredible thing. Okay, so we've turned around our spaceship and we're going to come back to Earth. We're going to fly out a little bit. Now, the other thing you need to know in this 30-second guide to the universe, it's a bit more than 30 seconds, is that the stars you see are only a tiny fraction of what there is in the universe. In fact, the stars are made from more hydrogen. So stars are basically made of hydrogen, quite a bit of helium, but mostly hydrogen. And so there's actually a lot more hydrogen floating about in the universe that for some reason failed to make it into stars. But even when we take that into account, we're still only seeing the tip of this iceberg. Or I was told recently it's like looking in the cathedral here or the chapter house and not accounting for the roof. Right? Apparently there's much more roof up there than you would know about. But here it's maybe even more, that we see a tiny fraction of the universe made of things like us, and there's a vast amount of it that's unseen. And we call this dark matter. So this is dark matter because it's not visible, but it's actually even more mysterious than that. It's not made of things like you and me. It's made of something. Recently they've turned on the upgraded Large Hadron Collider in Switzerland, and the aim is they'll actually manage to make a little piece of this other form of dark matter. I hope they will. It's going to be very hard to do that. So the universe is full of this dark matter, and if I make a little pie chart, this is how much normal matter, basically human beings, heavy elements, iron, things that make the Earth, stars. Mostly this is this sort of fluffy hydrogen and helium that failed to make stars. And actually, the current calculations suggest this is only about 4% of all the matter in the universe. And 21% is this dark matter that fits in here, vast amount. Now, these two things actually turn out to be really important in our current explanation of the order of the cosmos. And I think without both of them, things wouldn't work. Now, these are kind of the good guys in the calculation. I'll show you the bad guy in a minute. Okay, and we talked about the Big Bang idea. Whether or not that really comes from Robert Grosseteste's work, we don't know. But the idea is that there's an explosion at the beginning of time. Exactly what form that is a matter of debate, that creates an initial expansion of the universe. So the universe explodes outwards. It's initially full of light and very hot material. It begins to cool down as it expands, and that's kind of trying to show you by these colors the universe cooling down. And we used to worry that we didn't know which of these fates. It was a very nice, appealing thing to explain the origin of the universe as the universe would expand outwards, slow down, and then start to collapse back on itself again. That would be great, because then you could say, oh, well, the universe doesn't have a beginning. It's just like Aristotle said, that the universe changes kind of states, goes through these cycles, and there's no beginning. It's always been doing these cycles, and we just happen to be lucky and about here, about now. Unfortunately, as we've measured more about the universe, we see that it's something a bit like these, where the universe expands outwards, it slows down, becomes quite cold, but it never recollapses again. So this creates this problem that the universe has a beginning. Now, I said that there was a bad guy in the room, and there certainly is. Our current measurements suggest that actually there's something we really don't understand. Dark matter we understood until CERN was not able to detect it. So we're still kind of hoping that next year or so the upgraded collider will find this. But there's something here that we call dark energy, and it's an extra form of energy in the universe that we really don't understand, and it has a nasty effect in that the universe never slows down. It accelerates, it actually expands faster and faster. And there's some slightly weird things about the universe that at the present day, the acceleration isn't too bad. We can still form stars and galaxies. But in the future, this is all going to go horribly wrong. Okay, now, we wanted to have some time for questions, so I'll go quickly. But what we can now do with the computer simulations, using much more complicated calculations than I needed to do to explain Robert Grosseteste's universe, I can actually try to calculate just like he did. I can program the computer with my best laws of the origin of the universe. I can set the computer going. Oh, he didn't have a computer, but you know, you get the idea. And see what happens, see how the universe works out. And so what I'm talking about is what we've called the Eagle Project. It's a collaboration primarily between Durham University and Leiden University, and is heavily supported by the Supercomputer Initiative in the UK, Iraq, and also across Europe. And so this is a picture of the universe that we find, but I'm going to show you in a movie in a minute. But just to show you how amazing this universe is, these are some galaxies that are made in our universe. And remember the one I was showing you before? This isn't a real galaxy. This is one that's actually calculated in that calculation from the laws of physics. And Hubble classified galaxies into all sorts of different types: spiral types, elliptical types, irregular type galaxies. And all those types of galaxies come out of our calculation. Okay, so let me think, how do I explain this in 2 seconds? Imagine you go to the beach. You go to the beach and there's this beautiful sandcastle, lovely towers, okay? You don't think, oh, it must have been a windy day and the wind blew the sand and it ended up looking like a sandcastle. You think, there must be some pre-formed intelligence that created the sandcastle and the order on the beach. And essentially, Aristotle's problem with this is that if you went back the next day, probably that beautiful sandcastle looks like this, right? That it's decayed down. Now, somebody very clever, Ludwig Boltzmann, came up with a mathematical way of formulating this problem, measuring how ordered a system was, so he could actually tell you how ordered the universe was. And he was able to quantify how time would change the order of things. So basically, you go from something that's pretty unique to something that's much less unique. There are lots of sandcastles that could have been jumped on and would now look like that, whereas there's probably only one sandcastle ever that looked as beautiful as that one. Okay, so you would think that the universe would start out looking nice, looking ordered, looking very special, and would end up in a state of disarray. And essentially, that's what Aristotle's problem is. What actually happens in the universe is really remarkably different. There's a funny effect that gravity, because it's a very strange force, it only pulls things together. It never pushes them apart. And so if we watch my simulation, you'll see that far from starting off in a uniform state and becoming, far from starting off structured and becoming uniform, over time we start out with something fairly uniform and end up with something structured. It's really amazing. Okay? Now, it turns out that Ludwig Boltzmann is still correct here, because the big structures that form, all the particles are moving very fast. So if you follow his mathematical description, this still agrees in some way that for something that only feels the force of gravity, the kind of order, the disordered state is the one where it's all put into big structures. Okay. So this is an image here showing how the dark matter in the universe grows and forms into structures. But the special thing about the universe is it contains the mixture of the two things. So if we now switch to the normal matter in the universe, it's sort of dragged along by the dark matter, formed into these very special places. But there are extra things that happen to the normal matter. When you make it very dense, it gets very cold instead of very hot. And when it gets very cold, that's actually makes it possible for it to form stars and planets. So here's some beautiful images. I'll just let it go around. And then what I want to do is I want to pick a little region and just zoom in, and we'll see how galaxies get made in this calculation. So in this, you see the creation of structure from nothing. It needs a little jog with the mouse. Come on, mouse. Okay, so now we're going to watch and we're going to see the dense kind of material that's actually able to make stars in the calculation. And so you see these whirling patterns, but the material is able to concentrate down at the center of the system. And the concentration is driven by the dark matter in the universe. And here we generate a nice looking spiral galaxy. In fact, in this image, you make lots of these and then they crash into one another and disrupt each other and form all sorts of different structures. Okay. And so if we now finally look at the stars in the universe that are created in this interplay of the dark matter pulling things together, creating structures, the normal matter being able to cool down and form stars in those structures, this very delicate interplay between the two creates the order that we see locally. Okay, so in this kind of calculation, we did a web forum, and people kept asking us all sorts of excited questions. How did we do these calculations? And then they wanted to know, well, did we actually form any people in this computer? And we said, no, of course not, of course not. And then they said, well, how do you know? And we said, well, we didn't expect to. And they said, well, how could you turn it off then? And I thought, oh no, we forgot to go to the ethics committee and ask whether, having created this universe, we could then turn it off. But then I have some smart PhD students, right, really clever, came up with the point that it's okay, we all put it on tape. So that's the equivalent that we put it in the deep freeze. If anyone ever comes up and says, you know, you look at we found a signal coming from your universe that created some kind of alien life form, we can always get it off the tape and put it back on the computer and put it back to life. So we're all right. Don't tell the ethics committee anyway. But so here we have this amazing thing that in the modern universe, there's this very special interplay with how we create the order of things. That there's the force of gravity gathering things together that's driven by this other form of dark matter that's responsible for creating order in the universe in really a very different way to that imagined by Robert Grosseteste and even Aristotle. So just to summarize, you know, Aristotle raised this question about how could something perfect be created? Wouldn't it fall apart over time? And I think Robert Grosseteste would have answered this by saying that, well, his perfected matter is just stable. It's going to last there forever, the spheres of the universe. The modern interpretation of this question isn't to go, that's a stupid question. I think it's a brilliant question. And we understand it by this peculiar interplay between the two types of matter in the universe. Now, there are opposing states. They basically have different ideas of perfection, that creates the order that we have here and now and leads to wonderful places like this. So, with that thought, thank you very much for listening.
Richard's very happy to take some questions.
Yeah, I'm very happy to be.
Thanks very much. Thank you very much for the very stimulating talk.
Pleasure to be giving it, especially here.
Quite. So firstly, if I may, is there any evidence that Grosseteste ever explicitly accuses Aristotle or Casuus III in terms of relating the cosmological argument for the existence of God to the ontology? So the causation is required, there to be something in the
Well, he certainly in De Caello tries to represent the idea that the universe was created and then provides the argument why that's well, I was going to say a stupid argument. He's more subtle than that. Now, it's interesting, if you read the modern commentaries on this, that Aristotle, for all his insistence on a discourse in which you were not personally invested in one particular outcome, dialectic, where's Mike gone? He was helping me practice this. The idea, nevertheless, in De Caello, he actually misrepresents some of the ideas in Timaeus, because I believe the point in Timaeus is that the godlike figure keeps the world perfect in some way. So, and that's how Timaeus overcomes the problem of the decay of the universe. And also, if you actually analyze Aristotle's logic, it doesn't actually work amazingly. And I think there's an idea that's missing in the commentaries about the fault in the logic is that if something can decay, it will decay. And I think the part that Aristotle doesn't explicitly say is this idea: the age of the universe is so big that it's inconceivable that we could happen to be here and now just before the universe starts to decay. And that's an argument we use in modern cosmology to argue about the likelihood of observing the universe we do. So, yes, I think is the answer, that he does explicitly take an issue with this position. Whether you believe his argument or not is a different question.
Thank you. If I may, secondly, this year is the centenary of the theory of general relativity being announced.
Yep. Yep.
I think November this year. 10 years on from the special relativity.
Mm-hmm.
And as we run, this is 5 years.
Yep.
So, is anything that you can say that Grosseteste was really hinting at in his work, or is that too much of a stretch?
That's too much of a stretch, right? So you've got to, what Grosseteste is really trying to do is to provide a physical model that explains what he knows about the world around him. And that's very much informed with the way earlier philosophers like Aristotle, like the whole Arabic tradition, how they've interpreted the cosmos. And he's trying to provide an explanation of that is in some way based. I mean, I showed you the mathematical version. He doesn't really do the mathematical version, but he proposes something that is a physical model that I would recognize as him doing physics in the same way. But general relativity, amazingly, these calculations that we do don't use general relativity. And I'll explain offline why not.
Another question.
What is the dark energy doing?
Oh, yes, I was hoping somebody might not ask me that question. So nobody knows, right? It's one of these weird things. Okay, it's the most odd thing about the universe. So the dark energy is making the universe expand faster and faster and faster. And it's really strange. There are theories that suggest that you could have this mysterious form of energy, so they're quite convincing theories. I would sign up to them. There's only one catch. The observed amount of dark energy is 1 followed by 60 zeros times smaller than that theory, which we usually take to be a sign that it's wrong, right? So that explanation doesn't work. So we don't really understand what it is. And the other thing that's very strange is if you'd lived when the universe was half its present age, no particular reason we couldn't be observing the universe in that time, you wouldn't have been able to detect dark energy. We wouldn't have been having a discussion because it would be so small that you'd have stopped doing astronomy. You'd have thought you'd have explained the whole universe before you found a measurement that indicated its presence. It's even more interesting if you ask what would happen if we lived twice, if the universe was twice its present age, and there'd be these astronomers sitting around studying all the properties of the local galaxy. It might not be a spiral galaxy, that's an interesting story, but there'd be this galaxy. And they'd discuss these theories, and they'd give some crazy guy a computer to try and calculate the origin of the galaxy. And the astronomers would look out and they'd see our galaxy, and there'd be nothing else because the universe had expanded so fast that all the other galaxies in the universe would be far too far away to be visible. But the guy with the computer would go, you know what? If we'd lived half the time in the past, we'd been seeing the universe full of galaxies. And probably everybody would have thought he was crazy and turn off the computer and tell him to do something more sensible. So the dark energy is really odd because we're doing astronomy and we are able to measure the dark energy, but we're still able to see other galaxies, and it doesn't make any sense that that's the case whatsoever. And the only thing that people come up with is to more or less go, well, if it wasn't like that, we wouldn't be asking the question, which is not a terribly satisfactory answer to this.
Thank you. Any other questions?
When you started off, you spoke of a shell
Yes.
with nothing else. Could you define nothing for me?
Yes. Yeah. That's a really, really good question, right? So nothing means not anything. But there's more to it than that. So Aristotle would have answered this by saying that there was no matter there, so you couldn't ask what the matter, what was there, because there was nothing. And, I could give this a modern interpretation by saying, well, I can't measure what's there because there's nothing to measure it with, right? So it really is nothing. Now, no atmosphere, no matter, nothing whatsoever. And it contrasts very interestingly with the modern notion of nothing, which we know if you go into the furthest corner of space, avoid everything possible so that you have nothing, that's actually full of stuff. It's full of stuff that appears for a fraction of a second and disappears. So it's really weird, nothing in the modern universe is actually full of stuff. And in fact, the dark energy is probably something to do with nothing. Okay? So you asked me a brilliant question.
Okay, we have time for one more question.
We've talked a lot about matter.
Yep.
I'd like to fire a question to you about time.
Yep.
We are now aware, I'll try and keep as short as we can, that time passes at different rates relative to two different observers at
Yep.
different points in the
Yep.
universe. Is it possible that that difference could be so great that what from our perspective has taken billions and billions of years since the Big Bang, from a different perspective at another point within the universe could actually have taken a much shorter time? Shall we say, for instance, 7 days?
Now, I'll come back. Can I answer the 7 days thing, right? Because that's a great question. I skipped over a slide, which maybe I shouldn't have done. Now, in Robert Grosseteste's time, there were 3 types of truth, all right? And one was that you observed something to be true. So, you might drop something and it falls to the floor, so that's true. Heavy objects fall downwards. Something might be, if you like, mathematically true. That I could show the sums of the squares on the sides of a triangle, of a right-hand triangle, add up to the long length. Those things are mathematical truths. But there's something that makes something even truer than that. And that's that it's written in the scripture, or even written by some authority. Okay? And Robert Grosseteste has a hard time, because you can see that he really appreciates Aristotle. Aristotle is such a cool guy to Robert Grosseteste. Sorry if I represented his language there. But, of course, there's a little problem in that Aristotle is not Christian, and so making him an authority would likely get you in the middle of a bonfire tied to a stick, right? So he has to be very careful of how he uses things from Aristotle. And we're always seeing in the text that he'll have this idea that's clearly Aristotle, but he daren't say Aristotle said this. Whereas often when it's some more established religious figure, he's very happy to cite the origin. Now, it's not a problem, okay? This new idea that the religious scriptures somehow create a conflict with science is a completely new thing. So Robert Grosseteste would have seen his efforts to understand the origin of the cosmos as being a way to try and get a better understanding of the scripture. And the scripture can be true, and it doesn't really have to mean 7 days. It's just trying to say 7 stages, or to describe how you might construct something. So for him, there's very rarely a conflict. The only one I think we found was where there was a criticism of Robert Grosseteste's description of how rainbows are created, because the Bible says rainbows are associated with evaporation of clouds. And so, then that's hard to argue that's an allegory or something. But usually you can accommodate all these things in one vision of trying to understand God's creation. And there isn't that conflict. Now, there's a first part to the question about relativity, and I have to think about that. You can certainly create tilted, things have to be causally ordered in the right way, but if an observer were traveling sufficiently fast, yes, these events could happen apparently in very quick succession, but you'd have to be traveling immensely close to the speed of light in order to do that, right? So.
Thank you very much, Richard.
Okay. Okay. Good. Well. Well, thank you very much for having me here, and thank you to Robert Grosseteste for inventing cosmology. Thank you.